Marquis, and this is Lab 3, Part 2, where we're finding the 2D flow of a cylinder with inviscous and viscous flow at a motor frequency of 30 and 60 Hertz. Specifically in this, this is going to be a video of inviscid flow. So the first thing we go here is to the geometry, which I've already imported from from SolidWorks. Make sure your analysis type is set to 2D. Then we're going to go to mesh. It's going to take a little bit to load. So right here you can see our wind tunnel. Here's where the cylinder would be. It's a cutout of the object. I've already meshed this before. The main thing we want to do is name all the sections. That's already pre-named. So right here we have the velocity inlet. We have the pressure outlet named. We have the outer walls, as you can see in red. And we have the object walls, which is the walls of our cylinder or circle. And for this mesh, we're not going to do anything too crazy. We're just going to go in, insert a method. Actually, we already had one here. Just do a all triangles method. For the geometry selection, we're just going to do this entire body face. And then for element size, we're going to go 0.001 meters, that is. And then you're just going to hit generate. Since mine's already generated, I don't have to do that. You would go in and hit update. This is already updated, so I don't have to worry about this. So I'll go into setup, hit OK. Hit double precision, and depending on how many cores you have, you can add more. It'll make the calculations go faster. I just put it at 8 for this one. So as you can see here, here's our wind tunnel. We have our velocity inlet and our pressure outlet. So first thing you want to go is go into mode. You want to make sure that energy equation is turned on. Hit OK for that. The next thing is going to be our model. So in this one, we want an inviscid model. Hit this top one and hit OK. And then we're going to just make sure our material, sure fluid is set to air, which it is in this case. Now we're going to go to our boundary conditions. Go to our velocity inlet. Right now our velocity inlet is set up for 60 Hertz. So this would be the magnitude if we were using 60 Hertz, and if it was 30 Hertz, I believe it would be like 1.9 meters per second, around there. So you hit apply for that. Close it out. Then one more thing that we're going to have to change specifically for getting a normalized coefficient of pressure is a reference value. So right here, most likely it's going to have 1. You're going to want to change the reference value, velocity, to your velocity in the test chamber. You do not want it to be referencing your inlet velocity or a velocity of 1. If that is the case, your coefficient of pressure will be off. Now the next thing we're going to do is initialize it. Initialize. After the initialization's done, we're going to run our calculations. I just have it set for 200 iterations. It'll probably take around 98, something of that. I just put 200 just to be on the safe side. Hit calculate. I'm going to stop it here. It's taking a little long. Let's probably go to, actually we'll wait. It'll probably go to 98 iterations, so we're almost there. It'll take, depending on how many processors you're using, it'll take longer. So I think I have mine set to 8. As you can see, it's taking quite a bit, so you can put more depending on your laptop or computer. If you use less, it'll probably take longer to calculate all this. We converge that 99 solutions. So after you do that, you can go into plots, go to XY plots, and specifically, we're going to want to look at the velocity in the X direction, and make sure you have object walls selected, and then you can slave and plot. See, this is what it looks like. Another major one you want to get is change this to pressure, change this one to pressure coefficient. Same thing, have object wall selected. Make sure it's in the 1 in the X direction and 0 in the Y direction. Save and plot that. And this should be about right. So we're within 1 and -3 for coefficient pressure is what we're looking at. While we're not exactly at 1 for a stagnation point, that could be due to either a bad mesh or not having the best contraction ratio when we're referencing our velocity. But generally, like I said, you want it between 1 and -3, which it is. So this should be good. Thank you, and that's all for this part of Lab 3.